Welcome back to another explainer. If you're a data engineer gearing up for a system design interview, or maybe you just really want to understand the nuts and bolts of distributed computing, well, you are in the exact right place. Today, we're taking a sledgehammer to a major data engineering myth, the idea of infinite scalability. We're going to look at the hard, cold engineering realities behind Apache Spark performance and explore exactly why the belief that just blindly throwing more hardware at a problem solves everything is frankly a fundamental junior mistake.
Okay, let's dive right into this. This is literally one of the most common traps you're going to face in an interview. Interviewers love using the specific question to test if you actually understand cluster mechanics and distributed systems, rather than just checking if you memorized some basic Spark syntax. See, there's this really common real-world assumption out there that throwing more hardware at a problem will linearly decrease processing time. It's easy to think that more executors automatically equals a faster Spark job. But if you're in a highly technical whiteboard interview and a system is running slow and your very first architecture proposal is to just bump up the executors from 20 to 100, you've probably just failed that question. So let's look at the hard data to deeply understand why.
Check out this real-world production scenario we pulled from the source material. We've got a Spark application tasked with processing exactly 2 terabytes of data. Now, with an initial setup of 20 executors, it knocks out the job in 42 minutes. When we scale that up to 50 executors, the runtime drops down to 28 minutes. Mathematically, that makes sense, right? That's a solid expected win, but pay super close attention to the plateau that happens next. When we double the compute power again, going all the way from 50 to 100 executors, meaning, by the way, we are paying for twice as much cloud infrastructure, the runtime only drops to 27 minutes. We literally threw twice the hardware at the problem, and we only shaved off 1 single minute of processing time. Why? Because the primary bottleneck completely shifted away from CPU computation. Once you hit that specific physical bottleneck, adding more executors provides absolutely zero performance improvement. In fact, in several architectural cases, it actually degrades your cluster performance. Reverse engineering this exact plateau is what we're going to conquer today. To absolutely nail this topic in an interview, you need a really solid mental map. So we've broken this complex problem down into 5 critical engineering domains you need to bring up during your whiteboard session: task and scheduling architecture, data movement and distribution, I/O and external constraints, hard limits and diminishing returns, and finally, the true engineering solution. All right, let's jump straight into section 1, task and scheduling architecture. And this brilliantly illustrates the golden rule of limited parallelism. Spark operates on a very strict mechanical rule. It executes exactly 1 task per partition, and each task requires exactly 1 CPU core. So let's say your input data frame has exactly 40 partitions. On the left side, with an allocation of 20 executors, Spark can run 20 tasks simultaneously, while the other 20 are queued up, just waiting in memory. But look at what happens on the right. If you blindly increase your cluster to 100 executors, Spark physically still only has those 40 tasks to execute. The mathematical reality here is that 40 executors are going to be doing all the heavy lifting, while the remaining 60 executors are just going to sit there, completely idle, burning your compute budget while contributing absolutely nothing. Adding executors cannot, under any circumstances, increase the parallelism beyond your total number of available tasks. Now, the second huge bottleneck here is the Spark driver itself. Think of the driver as the central brain of your distributed application. It's totally responsible for scheduling tasks, managing the DAG, and keeping track of state across the whole cluster. But this central brain has strict physical limits. If you have a massive number of executors, the driver is suddenly hit with an O of n or even O of n squared communication complexity. It's got to manage way more task scheduling, process this never-ending flood of heartbeat messages to make sure the nodes are alive, handle a huge spike in remote procedure calls, and track exponential amounts of metadata. At a certain scale, all this network coordination severely cripples the driver's own CPU. It hits a breaking point where it spends way more time just coordinating the cluster nodes than it does scheduling actual useful work. Now, as an engineer, you might be thinking, well, simple fix. I'll just repartition my data into thousands of tiny partitions so all 100 executors stay totally busy. Actually, scratch that. Doing that introduces a fatal flaw known as tiny task overhead. If the work is chopped up into way too many tiny tasks, Spark ends up spending a huge chunk of its CPU cycles just managing those tasks instead of actually processing your data. We're talking about the strict millisecond costs of context switching. There is a fixed physical cost to spin up and tear down a task. If the task itself only takes, say,
say, 2 milliseconds to process a tiny data partition, but it takes 10 milliseconds for the driver to schedule, serialize, and deserialize that task over the network. Your cluster is operating at a massive efficiency loss. Instead of crunching through your 2 terabytes of data, your hardware is just burning all its energy managing the tasks themselves. Moving right along, let's hit Section 2, Data Movement and Distribution.
So, one of the absolute biggest reasons a Spark app stalls out is data skew. This happens when your underlying dataset isn't perfectly distributed, meaning one specific partition ends up holding significantly more data than the others. In this scenario, most of your executors are going to finish their tiny partitions super fast, and then they just go idle. Meanwhile, one unlucky executor is stuck grinding away trying to process this massive bloated partition. To really get why this is a bottleneck, you have to understand the sync barrier. Because of how Spark stages are built, the next execution stage physically cannot start until the final, slowest task in the current stage finishes. It creates this massive roadblock. Increasing your executor count to 100 does absolutely zero to solve data skew, because the workload assigned to that single overloaded core is still fundamentally uneven.
Next up is the notorious shuffle bottleneck. This one is absolutely crucial for system design interviews, so let's walk through it step by step. First off, wide transformations like group by, join, distinct, or order by, they explicitly trigger a shuffle. Second, during this shuffle, executors have to execute an all-to-all network communication pattern. Basically, every executor has to map, partition, and swap data across the physical network with every single other executor. Third, if you've artificially bumped up your executor count to 100 or 200, you are exponentially increasing the matrix of network connections and the sheer volume of temporary shuffle files that have to get written to disk. And finally, the physical overhead of opening, writing, and tracking thousands of these files over a network starts to completely dominate your execution time. Adding executors during a heavy shuffle operation will practically guarantee your job runs slower, just because of the massive surge in cross-cluster network chatter.
All right, let's look at Section 3, I/O and external constraints. You know, in a mature data pipeline, the CPU is actually rarely the bottleneck anymore. You really have to look analytically at the balance of your hardware utilization. If your application is spending the vast majority of its time just waiting for data to arrive, like your physical network bandwidth or disk I/O is totally maxed out, but your CPU utilization is sitting there nice and low, you aren't compute bound. You are strictly I/O bound. And if an interviewer asks how you'd prove this, you tell them you'd look straight at the executor task time metrics. If the actual computation time is tiny but the wait time is huge, adding more executors just means you're adding more expensive CPUs to the cluster that are going to do nothing but twiddle their thumbs waiting for disk or network reads to finish. On top of that, you absolutely have to analyze where your source data is actually coming from. Spark pipelines usually ingest data from external dependencies. Think AWS S3, HDFS, relational databases, Kafka event streams, or REST APIs. And here's the kicker. Every single one of these external systems has its own rigid throughput quotas and concurrency limits. For example, if you're reading from a relational database, you are strictly limited by that database's maximum allowed concurrent JDBC connections. If you blindly scale your Spark cluster to 200 executors, well, 150 of those executors might just get instantly rejected by the database firewall. If the external system physically cannot deliver data any faster, your internal Spark cluster size doesn't matter at all. Which brings us to Section 4, hard limits and diminishing returns. So the crucial point here is something people easily forget. A distributed cluster is still a physical entity. It is totally bound by finite hardware resources. There's a hard physical ceiling on available CPU cores, total RAM capacity, the actual network bandwidth of your data center, and the IOS of your storage desks. Think about network saturation. Every physical server rack in a data center has a maximum bandwidth limit, like a 10 gigabyte switch. You physically cannot push more bytes through that copper wire, no matter how many virtual executors you spin up in your cloud console. Asking for additional executors when these physical resources are already maxed out accomplishes absolutely nothing, except creating endless thread weights for hardware resources that just do not exist. Plus, any senior engineer needs to be super familiar with Amdahl's law. This law governs the strict mathematical limits of parallel computing. Basically, not everything in a Spark app can run in parallel. There are strictly sequential operations fundamentally baked into the Spark engine. Query planning and DAG generation are perfect examples. The driver has to calculate the entire lineage and execution plan linearly before any of the worker nodes can even start their tasks. Task scheduling and gathering the final aggregate results back to the driver node, those also happen sequentially. So as you add more executors, sure, the highly parallelizable part of your job might speed up, but the time taken by the sequential portion doesn't change at all. That baseline sequential overhead acts as a hard mathematical ceiling on how fast your application can actually go. And finally, let's bring it all home with Section 5, the true engineering solution. Now, what's really interesting about this slide is the core engineering philosophy here. Identify the actual bottleneck using the Spark UI. A true professional does not guess. They don't just blindly turn up the executor dial in a config file and cross their fingers for a faster runtime. The absolutely correct architectural approach is always to rigorously inspect the execution metrics. You have to open the Spark UI, deeply analyze the execution stages, check the task duration distributions across percentiles, look at the exact shuffle, read, and write payload sizes, and identify the specific physical bottleneck holding your system back. In advanced engineering, hard data dictates the solution. Once that Spark UI shows you the empirical truth, that's when you apply targeted, specific engineering optimizations. If your task execution parallelism is the limit, you dynamically optimize your partition count using repartition or coalesce. If shuffle network overhead is killing your performance, you actively tune your shuffle behavior. Maybe you convert standard sort-merge joins into broadcast hash joins to just bypass the cross-cluster network shuffle completely. If worker tasks are crashing with out-of-memory errors, you meticulously manage your memory allocations and executor core ratios. And if the UI proves you've got severe data skew, you don't just buy more hardware, you apply a salting technique, appending a random key to evenly spread that overloaded data across the cluster. These 4 precise actions, these are the actual engineering solutions to performance issues. So, we've systematically covered the strict architectural limits of the driver, the massive data movement traps during shuffles, the hard wall of external I/O connections, and the undeniable mathematical reality of Amdahl's law. You now know exactly why the infinite scalability myth is completely busted and mathematically impossible. So I'll leave you with this final thought. The next time you're sitting in a high-stakes system design interview, or the next time your production Spark pipeline slows to a total crawl, you aren't just going to blindly provision more hardware, you're going to immediately dig into the execution data. What will the Spark UI reveal about your true bottleneck? Thanks so much for joining me on this explainer. Keep learning, keep engineering, and I'll catch you in the next one.